Greetings, my friends. In this video, we are going to discuss a very interesting phenomena in physics. Uh, you must have observed that when a gardener waters the plants in the garden, he usually covers the outlet of the hose pipe with his thumb such that the water that comes out of the hose pipe is has a larger velocity compared to when the thumb is not used. I will show you an image. Over here we see the thumb is used to partially close the hose pipe, and the water that comes out is ejected with a higher speed. So this is something we must have observed, and perhaps we must have applied this ourselves. Now a question arises: how is that with just using our thumb we are able to increase the speed of water? Shouldn't there be some requirement of external force to increase the speed of anything? So how is this happening? So this is an interesting question. So in this video we are going to address this question. One more observation I would like to discuss, which is related to this, what we just talked about, is this: we all we all play in our childhoods uh, with paper boats. So we all have done this, what you see on the screen. So now as a grown up you can still do something which is as follows. In the rainy season there are pools and puddles all over the place. So try to do this. This is the upper view of a brook, a small flowing water, upper view. So assume or find a place where the water flows in this manner. In this manner, in the sense, this is the path in which the water is flowing. It is not uniform. The width, this width, is not uniform for some reason. So water is flowing in this direction, for example. Then what we can do is place a paper boat somewhere like this, some on this water, and you will notice that as you place the paper boat, the boat will go with the same speed as that of the flowing water in this direction. uh, we will observe that the speed of the boat is smaller in the areas where the width is larger, and as it approaches the narrower parts the speed of the boat increases, and again as it enters the broader parts the speed of the boat decreases. So this is another phenomena where there is an apparent acceleration, not apparent acceleration, I mean there is an acceleration. The boat increases its speed, or the speed of the boat is increased when it passes through narrower parts, and this happens all the time. So somewhere ahead, if you have even broader parts, the speed of the boat will even decrease. Then later, if you have even narrower parts, the speed of the boat will even increase, and so on and so forth. So this is another observation which is related to the previous observation. Now we are going to discuss why, or what is the physics behind these observations. So let us see. Consider a pipe with non-uniform cross section. So this is a pipe. The cross section is not uniform as it is clear from the diagram. Now assume there is some amount of water that goes in from left to right in a certain amount of time, delta t. Or let us assume that water is flowing from left to right and it is supposed to pass through the pipe. All the water is supposed to pass through the pipe. Now what we can tell about this situation? We can tell that the amount of water that goes in is the amount of water that comes out in a certain amount of time. Why? Because there is no accumulation of water inside the pipe. So whatever amount of water that goes in from left and enters into the pipe, that no part of that water stays inside the pipe. Everything comes out. So whatever goes in comes out. So we can write this. So let me write this, because this is going to be the underlying principle with which we will begin our analysis. So let me write here, whatever goes in comes out. So this is going to be our principle. As we understand from common sense that water is not accumulating in the pipe, and hence what I have written on the screen is true. So now let us try to figure out where this can lead. Assume that in a certain time delta t, a certain volume of water enters in. So let this be the volume of water that enters in. So this is the distance. Let me call this as x1. Let me call the area of cross section, as a1, and assume that through x1 the area of cross section is same. So it is a1 here and it is a1 here as well. Both are equal. So let us assume the water that goes in at time t is equal to 0 covers a distance of x1 at time t is equal to t, and we are interested in the amount of time t minus 0, which is basically t. So what is the volume that goes in? Let me call the volume that goes in as V1, because we are talking about this area. Everything in this area will be denoted by subscript 1. So V1 is equal to A1 x1. It is like a cylinder. I mean, this area, shaded area, looks like a cylinder with A1 as the base and x1 as the height, and volume of a cylinder is area of the base multiplied by the height. So this is the volume. Now as the water passes forward, as all the water passes forward, assume that water has reached over here. By the way, we are considering a continuous flow. I mean, the water is continuously entering from left and it is supposed to come out from the right, because there is no other way, as the pipe is totally enclosing the water. So there is a continuous flow. So as time elapses, the water reaches this end. So what is the amount of water that comes out from the other end in the same amount of time delta t? So that volume can correspond to any value of x. For example, it can be this volume. I mean, it can be this shaded volume, or it can be this shaded volume, It can be more, it can be less, it can be this shaded volume, and so on. So let us assume it is some volume. We don't know what it is. Let us say that this is some volume. This much volume comes out in the same amount of time delta t. And let us assume this length is x2. We don't know what is this. And let us assume that throughout x2 the area of cross section is the same. Now what is the volume that comes out? The volume can be written as A2 x2. Now based on our sentence that we wrote, whatever goes in comes out. Based on this sentence, we can safely write that V1 is equal to V2, because these are the volumes involved which take up same amount of time to go in and come out. So we have here V1 is equal to V2. So further we can write A1 x1 is equal to A2 x2. Let me create some space. Okay. Now with this equation we can do something which will lead us to something insightful. What I do is I divide both sides by delta t. This is the same delta t that we talked about over here. The amount of time in which the volume V1 goes in and the amount of time in which the volume V2 comes out. So what we have here is, if you notice this bracket, x1 by delta t and x2 by delta t, what do they tell us? What is distance upon time? Distance upon time, as one can recall, is nothing but speed. So if I say x1 by delta t, what do I mean here in this picture? I mean the distance, this distance which is x1 divided by the amount of time it took to travel x1 is nothing but the speed of water in this area. So the speed of water in this area, if we call it V1, where V stands for velocity, is this. So V1 is the velocity with which the water is moving forward at the inlet. And what is x2 by delta t? x2 by delta t is x2 is this distance from this starting point to this end point. So distance is x2, the time taken is delta t, and hence the speed with which the water flows in this section, in this area, is nothing but x2 by delta t. So x1 by delta t is v1, which is nothing but the speed of water in the inlet area, and x2 by delta t is the speed of water in the outlet area. So I can substitute these values in the above equation. So we have A1 V1 is equal to A2 V2. So this is what we have arrived at. Now what this equation tells us. If I modify this equation in the following manner, then this tells us something insightful. It is telling us that the velocity is inversely proportional to area. From the proportionality concept in mathematics, do you see the subscript 1 is in the numerator and on the RHS it is in the denominator? subscript 2 is in the denominator in the LHS and is in the numerator in the RHS, and hence we can safely write that the velocity is inversely proportional to the area of cross section, and that is exactly what we find in these observations. So when a person or the gardener partially closes the outlet of the hose pipe, he is basically reducing the area of cross section, and if the area of cross section goes down, then the speed of flow of water should go up, and that is exactly what happens. And also in the boat example that I gave you, when you observe the boat passing through a narrower part of the brook, you will notice that the speed of the brook is higher because the area of cross section has reduced. So area of cross section goes down, the speed of water goes up, and accordingly the speed of boat goes up. So this is how we understand the physics behind these two observations. So I hope this concept is clear. By the way, what we wrote here, whatever goes in comes out, can be written in more technical terms, and when you write that statement in technical terms, that statement is called the principle of continuity, and this equation which we have arrived at is called the equation of continuity. So those are the technical terms, technical names we have given to this equation. So I hope the video is liked, and this video was insightful. I thank you for watching.